So hello everyone, welcome back to the channel. So yes, it's been a while that I have posted the last video, but yep, I'm again back again. So anyways, let's take a look at this beautiful question from the Codeforces round 975 division 1, and it is the third question from the round. So we are given, okay, so there timestamps in the description or below the video. I want you to try this question on your own, give your all to it, and if you are not able to solve the question, here's the solution. So you are given a tree with n nodes rooted at node 1. In this problem, a leaf is non-root node with degree 1. Okay, makes sense. So in one operation, you can remove a leaf and the edge adjacent to it, possibly new leaves appear. Okay, so that's kind of obvious. So what is the minimum number of operations that you have to perform to get a tree also rooted at node 1 where all the leaves are at the same distance from the root? Okay, so let me explain this part as well. So possibly new leaves appear. So that's pretty simple. So consider this tree. Okay, so now if you remove this node, okay, if you remove this node and the edge adjacent to it, then our tree will become like this. Did the new leaves appear? No, just this one vanished. This and this are the only nodes remaining now. But when I remove this vertex and this edge, then my tree becomes like this. Now you can see this is the new node which has appeared. So that is basically the statement saying. So let us take a look at the sample test case. Okay, so here they have really depicted the process in a nice way. So this is the first input and this is the second input of the tree. So see here, so if you want to so let me take this picture. Can I take it to the Microsoft whiteboard? Yep, I can. Okay, unable to insert image. Okay, so okay, uh okay, no problem. So let me draw the tree itself. So it won't take too much time, I believe. Was this the tree? Yes, I think that's correct. Okay, so optimal answer is okay. Before calculating the optimal answer, let us suppose we want to keep the nodes at depth 1. Okay, we want to keep all the leaves at depth 1. All the leaves at depth 1. So basically I want these two nodes as leaves, and now I want to remove this edge and this vertex, this edge, this vertex, this edge, this vertex, this edge, and this vertex. So how much edges do I need to remove? 1, 2, 3, and 4. Or how many vertices do I need to remove? 4. So for depth is equal to 1, your answer is going to be 4. What about depth is equal to 2? So for depth is equal to 2, you can notice that this node and this node should remain, right? So what are you deleting then? So depth is equal to 2. Okay, so you will be deleting this vertex and this node, this vertex and this node, this vertex and this node. So for 2 you got to perform 3 operations. What about depth is equal to 3? For depth is equal to 3, you will keep this node and this node. So you gotta remove this vertex and edge and this vertex and edge. So for 3, your answer is going to be 2. So in all of these numbers, my 2 is the minimum number of operations, right? So for this tree, my answer is going to be 2. Okay, so similarly for this tree, you can notice that depth 2 is the optimum choice. Okay, so here also 2 cuts are, or whatever it is, 2 operations are required. Okay, so uh, what my intuition tells is that, what my intuition behind to solve the problem is, states that, okay, so what's happening? Okay, so my intuition tells me that, so if I want to keep my nodes or leaves at depth 1, so if I want to keep them here, I want to remove all these things, right? All these things. Okay, makes sense. So I want to remove all the nodes which are at higher depth than my desired depth, right? Okay, makes sense. And suppose so this is the first observation, so let me write it down. I have to remove the nodes which are at the higher depth than my desired depth, right? Than my desired depth. Okay, this is the number one observation. Okay, so from this observation, what I can notice is that, so suppose the leaves which okay, so the nodes which will get removed in the process, if I select the depth to be D, so final depth, if I select it to be df, so I will remove all the nodes, whose depth of the node is greater than my final depth. Okay, makes sense? Yes, it absolutely does. And yes, for the second observation, we have to consider another case. So let me take this right down here. Okay, so let me erase that. Okay, so if I want to select my df as 2 now, so in the case previous case, we took df as 1 and arrived at the observation number 1. If I take df is equal to 2, if I take final depth as 2, so I want to preserve these nodes, this thing and this thing. So uh, from the first observation, I can notice that if my node, if it remains, then its depth should be less than or equal to final depth. Make sense? Okay, this is the first inequality. This is not gonna work. This is what we want. Okay, so yep, for df is equal to 2, what I can notice is that, so listen carefully, this is the most important part of the solution. So for df is equal to 2, my these nodes, this node and this node, is gonna be eliminated from observation number 1, right? So these two nodes are gonna get eliminated through the observation number 1. But I want to also remove this node. Yes, you're true. Yes, definitely I want to remove this node, but is my observation number 1 helping me? is my observation number 1 helping me? So this case is holding, right? For this node my observation number 1 is holding. So but I want to remove that, so I want to make one another observation. I want to make one another observation, and that is number 2 observation is that. So think about this. So this node is gonna be removed, right? But this node is surviving, right? Why is it surviving in this process? Because the depth of the leaf, the maximum depth of the leaf in its subtree, again I'm repeating, the maximum depth of the leaf in its subtree, which is 3, the maximum depth of leaf in its subtree, which is 3, is greater than final depth. So max depth of leaf in subtree. So if this is greater than or equal to, okay, so okay, wait, I wrote the symbol wrong. So less than or equal to, so if my maximum depth of a leaf in subtree is greater than or equal to final depth, if this is the case, then my node is surviving, so from second observation I can write the strong assumption that df is less than or equal to max height of leaf in subtree of the node, max height of leaf in the subtree of that node. So from the observation number 1 and from the observation number 2, so I can get that my df, the final depth, should be between these two numbers. Okay, so these nodes will survive, so you might be thinking, so you might be thinking that I am telling you to iterate over every depth from 1 to whatever it is. It can be maximum n minus 1. So you want to, you are saying that I am saying that you will iterate over every depth and do this thing, but won't it cost TLE? Maybe it will, but there's a very clever technique, involved, and that is delta encoding. Very simple yet very effective technique, delta encoding. Some people call it a difference array. Okay, it is somewhat informal name, difference array, but this is kind of classic name, delta encoding. So what this delta encoding states is that, so let me give you a brief overview of delta encoding. So bear with me. So let us kind of deviate from our problem to understand what the delta encoding is. So for those of you who you already know the delta encoding, can skip to the following part of the solution. Okay, so suppose what I run is that, so I run a shop. Suppose I run a shop. This is my shop. Okay, it doesn't has a door, but okay, maybe this is the window. Anyways, so this is my shop, and suppose at 1 unit of time, so I start the timer from 0. At 1 second, Okay, at first second, one consumer arrives and he leaves at the fifth second. Okay, so another customer comes at 2, leaves at 6. Another customer comes at 3 and leaves at 4. Okay, another customer came at 2, left at 3. Another customer came at 3, left at 5, or let's say 7. Okay, so now I want to know what was the, now my question is, what was the maximum number of people, I had in my shop, or was there in my shop. Okay, so this is kind of a classic problem and it can be solved by sorting, I believe, but there's a very clever technique named as delta encoding. So what I'll do is that, so this is my first second, this is my second, and this is my third one, this is the fourth one, this is the fifth, this is the sixth, this is seventh, and this is the eighth second, and of course it is the start time 0th second. So what I will do is that whenever my customer comes, so customer is arriving at 1, so I will do plus 1 at the position 1. So at the time 1 I'll do plus 1 because there's a customer at the time 1 in my shop. Okay, so I'll do plus 1, and he was there till 4 and he left at 5. Okay, wait, so okay, suppose he was there till 5. Let us frame the definition of this interval as like this. So he was there from 1 to 5 and he left at 6. So my at 6 I lost my customer, I lost my one of the customers. Okay, makes sense. So for second customer he arrived at 2. Okay, and I lost him at the 7th second. Okay, then minus 1. Again, I had a customer at 3. Okay, so plus 1 at 3, and I lost him at 5. So minus 1 at the 5. I had a customer, one more customer at 2. So I'll add plus 1, and I left it at, he left my, or she left my shop at 4th second. So it is minus 1. I lost one customer at the 4th second, and again there was a customer coming in at the 3rd second and he left the shop at the 8th second. Okay, so this is what I call the delta encoding array. So I have encoded the differences, I have encoded the differences that each customer made to my customer count. Okay, and now what will I do? I will take the prefix sum. I will take the prefix sum of the array delta encoding. So how will it look like? So let's see. So let me take this part right here. Okay. Good. So if I do the prefix sum for 0, 1, 2, 3, 4, 5, 6, 7, 8. So let's go. So basically my delta encoding array is 1. So I'm just adding these values: 2, 2, then minus 1, minus 1, minus 1, minus 1, minus 1. Okay, yep. So this is definitely for 0, 1, 2, 3, 4, 5, 6, 7, and 8. So let's start taking the prefixed sum. So 0, 1, 3, 5, 4, 3, 2, 1, and 0. So what I can notice from here is that the maximum number of customers in my shop were 5. were 5, and those were at the third second. Those were at the third second. Okay, and that's the very important use of the delta encoding array. And it can also tell you that at the 6th second my shop had the 2 customers, at the 1st second my shop had the 1 customer, at the 8th second my shop had the 0 customers, at the 4th second I had the 4 customers in my shop. That's it. That's the very important use of the delta encoding array. So I hope it is clear. Okay, so let us again head to our problem. So our problem was like, so is this looking familiar to you? Is this looking familiar to you? So you want to find, the depth. So you want to find the depth such that the nodes satisfying, this criteria, was maximum, Okay, makes sense. Yep, it absolutely does. So this was the thing. So why I want to take the maximum of the nodes? Because I want to preserve them. I want to preserve the maximum nodes possible, and I want to remove the minimum nodes possible, because I want to minimize the cost of the operations, right? So that's why. So that's right. So that's why I want to preserve as many nodes as possible. So this is basically the thing. Then I'll again use the delta encoding for this purpose. I will calculate the dn and mhlisn for the every node, and make the delta encoding array for that vector of this type of pairs, Okay, so I will make the delta encoding vector, take the prefix sum, and like this, and just like this I will find the maximum number of nodes that were surviving for any of the depth, and basically then I have found my answer. Yep, makes sense. Okay, so let us take a look at this sample test case. So let us try to do the delta encoding based on this beautiful tree right here. So looks pretty beautiful. Okay, let me clean it up. So for this node, let's number the nodes. 1 2 3 4 5. Okay, wait, let's follow the convention. 1 2 3 4 5 6 7. So 2 is here, 3 is here, 4 is here, 5 is here, 6 is here, and 7 is here. Okay, makes sense. So so we will exclude the node 1 from our calculations. Okay, so because we want to always keep it, okay, so we will start from the 2. Okay, so we will calculate depth of node and maximum height of leaf in subtree of that node. Okay, for 2. Okay, let's draw the straight line. Okay, so for 2. Okay, anyways, so for 2 the depth is 1, for 3 depth is 1, for 4 depth is 2, for 5 depth is 2, for 6 the depth is 3, for 7 the depth is 3. Okay, and what about the maximum height of maximum depth? Okay, height or depth, however you want to perceive it. Okay, so mhlis for 2 is 3, right? Because this is the node with the maximum height in the subtree of 2. Okay, makes sense. Yes, so 3. For 3 it is 1 because 3 itself is a leaf. 3 itself is a leaf, so it will be 1. So for 4 again it is going to be 3 because 6 is the MHLIS enough for 4. So for 5 it is 2 because 5 itself is a leaf, you can say. For 6 it is 3 again because 6 itself, and similarly for 7 it will be 3. So that is basically gonna be the thing. And yes, let us delta encode the things. So for what is the maximum value here? 3. So we want to calculate our delta encoding till the fourth depth. Okay, so 4, 3, 2, 1, and yep, let's start it. So plus 1, and here minus 1, here plus 1, and here minus 1, here plus 1, here minus 1, here plus 1, here minus 1, and for both of these things it is gonna be plus 1 at 3, plus 1 at 3, and minus 1 at 4, and minus 1 at 4. Okay, so how is my delta encoding looking like? So it is like 0, 2, 1, 1, and 4. Oh, minus 4. Okay, minus 4. Beautiful. So let's take the prefix sum. 0, 2, 3, 4, and 0. Yep, makes sense. Now what I can notice is that, so for some depth, I don't know for what depth, so that's why I don't need to iterate over the depths. I don't know for what depth this these four nodes are there in my tree, are there in my tree, these 4 nodes except one. So this is also basically the important point, except one. Okay, 1 is gonna be always there. So for except 1, these are my statistics of the delta encoding array. Okay, so except 1, 4 is the maximum number of nodes surviving. So maximum number of nodes surviving is 5, basically 4, and 1 is compulsory to take. So if it is 5, then I have to remove 7 minus 5 because 7 is the number of nodes in the tree. I have to remove 7 minus 5 equal to 2 nodes, equal to 2 nodes. Yep, so answer is going to be 2 for this test case. Yep, it is 2 for this test case. Okay, makes a lot more sense, I hope you understood it all, and I definitely recommend you to try delta encoding yourself on this second input of the tree, to get the maximum grasp of it. Okay, it is such a beautiful technique. So yep, let us head directly towards the code. So let me show you what you can say, the practical of this delta encoding array. So let us take a look. So DN and MHLIS. So let us take a look that if they are made correctly or not for the first test case. Okay, so these test cases doesn't really matter because we are taking input till here only. If you keep in this file or don't keep it, it is basically the same. Okay, let us check. So yep, run. So 0 1 1 2 2 3 3. Okay, 0 1 1 2 2 3 3. 0 is basically the depth of the first node. Okay, so and our MHLIS for n is 3 1 3 2 3 3. So 3 1 Okay, wait, 313233. Yes, makes a lot more sense, and MHLIS for 1 is absolutely 3, and our answer is just basically 2. If you want to check how the delta encoding looks like, here is the thing. So less than or equal to, okay, n, because our depth is maximum n minus 1, and it can go till I is less than or equal to n, so value in the delta encoding array. So okay, uh, this is before taking the prefix sums. Notice that I have took the prefix sum here. So let me erase this for the better clarity. So here we go. So see here. So so for so basically our DE array is 211 minus 4. Is it? So 211 minus 4. Yep, makes a lot more sense. And what is it after the prefix sums? Okay, so that is basically gonna be the obvious thing. So it is gonna be the one we have calculated. Let us, okay, what happened? Okay, let us remove this guy and let us check it. So it should be 2 3 4 and 0. So is it? Yes, 2 3 4 and 0. Yep, and that's the thing. And here I am calculating the maximum nodes surviving, and maximum nodes surviving plus plus, this plus plus is for the number one node. Okay, so yep, and basically you will output n minus maximum nodes surviving, and basically you have to clear up the things in the sense of the, because I'm declaring them globally, I have to clear them up for the next test case. Yep, makes a lot more sense, I believe. Yep, and let me take you through one more very interesting observation, so hang with me. So this submission this submission doesn't give TLE, it is accepted, okay, and this submission gives a TLE on test case 2. So let us compare what's the difference. So copying this thing, Codeforces provides the inbuilt difference checker, you can say. Okay, I want to copy this thing, copy and compare it with this. I think this is the same number that I copied. Yes, and compare. Okay, so see here, everything's same, but the one thing, see here in this line, just it makes a lot more difference, that if you initialize the delta array with the small n or the big N. I don't know why it made a lot more difference, but it did, for whatever reason it did. Okay, and yes, so that is basically one more important interesting observation. So try to optimize whenever you can, wherever you can. Okay, so yep, that's the thing. And very thank you for watching my video. If you are watching till here, I really appreciate your patience and the attention span. And yes, very much thank you for watching this video. I hope you learned something new, and if you indeed did learn something new, consider liking this video, sharing it, and staying subscribed to our channel, staying tuned with our community. So yep, see you again surely. Take care.